Let's apply our efficiency equations to another problem. This problem is very similar to one that was found in homework 12. In this problem, we have a worker who is pressure washing a deck 5.8 meters above a koi pond. The pressure washer produces an 8 liter per minute stream of water through a nozzle that has a diameter of 2.54 centimeters. A 12-volt power supply is used to electrically power the centrifugal pump, which draws from water from the pond. Assuming a 38% efficient system, we want to find the amount of electrical current that the battery must supply. In order to start this problem, I recommend that you write down in a list form all the known information that is given through the context of the problem. We know that a worker is pressure washing a deck 5.8 meters above the koi pond, and we know that the water is coming from the koi pond. So that 5.8 meters is our pump head. Remember, pump head is measured from the water level of the reservoir tank to the exit of the nozzle. So pump head is 5.8 meters. The pressure washer produces an 8 liter per minute stream. When we have a liter per minute, those units are flow rate. So our flow rate is 8 liters per minute. And then we also know that the diameter of the nozzle where the water is exiting is 2.54 centimeters. Additionally, in the problem statement, we're told that there's a 12-volt battery supply. So our voltage is 12 volts. And we're also told that the efficiency of the system is 38%. Before I start working this problem and trying to plug in the information into any equations, I recommend first checking your units of the values that you wrote down. Remember, you want to work in the metric system. So for our pump head, we have 5.8 meters, and that's the units that we want our pump head to be in. Our flow rate is in liters per minute. 8 liters per minute is a great way to visualize how the water is flowing through the system. We can see that it will pump 8 liters per minute. However, in our calculations, we want this to be in meters cubed per second. So that's a term that we need to change. So we know that we want, instead of liters per minute, we want meters cubed per second. We know that there is 0.001 meters cubed in 1 liter. We also know that in 1 minute, there are 60 seconds. That gives us a value of 0.0001333 meters cubed per second. Our diameter of our nozzle is 2.54 centimeters. We don't want centimeters, we want meters. So we also have to convert that as well. We know that there's 100 centimeters in 1 meter, which makes this 0.0254 meters. Our voltage is 12 volts and our efficiency is 38%. Those units are fine. Now we're trying to find the electrical current that the battery must supply. Thinking through our list of equations, the equation that has current in it is the efficiency equation. We are also given information related to that equation. We have efficiency, we have voltage, we have pump head, we have flow rate and diameter, which aren't explicitly in the efficiency equation, but they are values that we can use to find other components of the efficiency equation. So I'm going to write down the efficiency equation. Efficiency is equal to weight times height plus 1/2 mass times velocity squared over voltage times current times time times 100%. Looking at this expression, we can identify the things that we have. We have efficiency, we have pump head, we have voltage. The other components we don't necessarily have, but we have information in order to find them. So looking at the weight, we know weight is equal to mass times gravity. Do we have any information that can help us find mass? Recall that mass is equal to volume times density. Looking at our flow rate expression, we know that flow rate is equal to volume over time. We wrote our flow rate in terms of meters cubed per second to be 0.0001333 meters cubed per second. So because of this, we're basically saying our time is equal to 1 second and our volume is equal to 0.0001333 meters cubed. We can utilize this to help us find our mass, because we can say mass is equal to volume, which is 0.000133 meters cubed, times our density of water, which is 1,000 kilograms per meter cubed. That gives us a mass of 0.1333 kilograms. So now we have our mass, which we can use to plug into our weight equation in order to find the weight. So now we know we have weight. And we also have mass now. Additionally, we have time. What is the time that we set for this volume? 1 second. Because we use 1 second here, we also need to use 1 second in our efficiency equation. The last thing we need to find is this velocity term. Recall that velocity is equal to flow rate over area. If we have flow rate, which is 0.000133 meters cubed per second, we just divide it by the cross-sectional area of the exit tube of the nozzle. The cross-sectional area is pi over 4, diameter, which we calculated to be 0.0254 meters squared. That gives us a velocity of 0.2631 meters per second. Now we have all the information to plug into our efficiency expression to calculate the current that is being asked for in the problem statement. Plugging in your known information, we have 38% efficiency. We have a weight, which is mass times gravity. Our mass is 0.1333 kilograms times gravity, which is 9.81 meters per second squared, times our pump head, which is 5.8 meters, plus 1/2 mass, which is 0.1333 kilograms, times the velocity, which we calculated to be 0.2631 meters per second squared, divided by voltage, which is 12 volts, times current, which is what we're looking for, times time, which is 1 second. Now you can rearrange the expression and solve for current. Current equals 1.665 amps. So the critical things to do when you're working these kinds of problems is to write down the key information from the problem statement, ensure that they're all written in the proper units, then look at your equations, determine which equation you need to use, and then identify the easily accessible information that was given in the problem statement and the information that you need to calculate on the side in order to plug into the equation and solve for the variable that's being asked for.